topic in quantitative methods basic concepts, and that's the time value money. Certainly a very basic concept when we're talking about financial analysis and finance theory. And so we'll take a good look at this. It's become the cornerstone of much of what we do in valuation in finance. So if I can advance the slide here. Our first learning outcome statement here, though, has to do with the interpretation of interest rates. What do we mean by that? Well, equilibrium interest rates are the required rate of return for a particular investment. So the price that an investment trades at in the marketplace in equilibrium is going to determine the rate of return on that, or at least the expected rate of return. Interest rates are also referred to as discount rates, and that's what we'll be talking about a lot in this segment, is how to discount future cash flows to get their present value equivalents. Now, we could also view interest rates as the opportunity cost of current consumption, because if I don't consume today and save and earn a market rate of return on those savings, then I can consume more in the future. At least that's the idea when interest rates are, real interest rates are positive. So it's that sense in which I'm giving up that growth and interest if I consume today. So that's why we say it's the opportunity cost of current consumption. Now, we use kind of a build-up model to explain interest rates. And here we're explaining the required or nominal interest rate on a security. And it's a build-up. It's a build-up from the real risk-free rate. Whenever we see real, that means adjusted for inflation or if there were no inflation. So the real risk-free rate is the increase in the amount of goods and services you could have at the end of the period in real terms. That's why I say goods and services. Now, our nominal risk-free rate, we're going to add expected inflation to that. So if we take these first two components right here, that gets us to what we call the nominal risk-free rate. Nominal, it's got the expected inflation premium built into it. Now, if this is a riskless security like a U.S. Treasury bill, then we'd be done. That's our return in the marketplace. But now, securities also have risk, so we add a premium for the risk of default. They may have less liquidity than Treasury bills, which have great amount of liquidity. So we could add a premium for that. And then if we look at longer terms, especially in the debt marketplace, the marketplace for fixed income securities, then we put on a maturity risk premium, which grows with the maturity of the instrument. So now let's define some rates here. The effective annual rate. The effective annual rate is how much your funds would actually grow over a one-year period. But sometimes we have compounding periods that are not annual. So that's what we're looking at here. Assume the stated rate is 12%. And what if we say we have semi-annual compounding? Then what would be the effective annual rate? Well, the technique here is very straightforward. We add that interest rate to 1. We take 1.06 because with semi-annual compounding, we've got 6% twice a year. So we 1 plus that 0.06, square it, subtract 1, and see, well, if we earn 6% every 6 months, compounded annually, our compound growth would be 12.36. The next thing to notice here is that with quarterly compounding, so 3% per quarter with a stated annual rate of 12%, would compound for 4 periods, and more compounding periods, a greater effective annual rate. With monthly compounding, it goes up even a little bit more. This is like on a credit card statement, right? If they told you that your annual percentage rate is 12%, in fact, they mean 1% compounded every month. So your effective annual rate would be 12.68% interest for any balances that were outstanding over a 12-month period. Let's take a look at an example. We've got a $100,000 CD with quarterly compounding, and it says it will return $123,528 in 2 years. What are the effective annual rate and the stated annual rate for this CD? Well, let's start with the effective annual rate. We know the ending value and we know the beginning value. So with your calculator, we can put in the present value as 100,000. The future value, note that it has to have an opposite sign. Your calculator assumes that if you put money into an account, you get to take it out later, or if you borrow money now, you have to pay it back later. So that's why the different signs. We've got no payments here during the period, no cash outflows from the account. We've got two periods, so we'll solve for the annual rate, and we solve this and get 11.14%. So this means at an 11.14% annual rate, compounded for 2 years, would turn 100,000 into 123,528. And what's our rate of return over the 2 years? Well, we can, since the numbers are based on 100,000, we can read it right off here. It's 23.528% over 2 years. So we could also do this just using arithmetic functions. Ending value over beginning value. Take the square root of that because it's a 2-year period, subtract 1, and get the annual compound rate. Now what's our stated annual rate? Well, remember the stated annual rate is going to be a little bit less, and we've got quarterly compounding. So what we really have to find is the quarterly rate of return. So there's 8 quarters in 2 years. Payment's still 0. Present value and future value are still the same. But now with n equals 8, we've solved for the quarterly compound rate of 2.676%. So a stated annual rate of 4 times that, 10.07%. If we divided that by 4 and compounded for 4 periods to get our effective annual rate, we'd get right back to 11.14%. Now we could also do this arithmetically. We just take ending value over beginning value here, take it to the 1/8 power minus 1 to get that quarterly rate, which is the same as we would find using the calculator functions, multiply it by 4 to get a 10.07% stated annual rate. Next topic here is a present value of a perpetuity. Now, preferred stock pays a dividend basically forever. Sometimes we call them perpetual preferred stocks. And this stock is going to pay $8 a year, and the rate of return is 10%. What is the value? Well, think about this. We could rephrase this question a different way and make it intuitively easier to understand. What if I said, what would I have to put in the bank at a rate of 10% in order to generate $8 a year forever? Because if we're going to generate $8 a year forever, we can't be taking any principal out. That has to be just the interest on this. So at a 10% rate, we'd have to put $80 in the bank to generate $8 a year in interest. Now, the present value is just the sum of the present values of all these future payments. So at a 10% discount rate, we discount that first one to its present value, dividing by 1.1, 1.1 squared, cubed, etc. So what we've really got is the present value of a series that goes on forever. Well, that's a little hard to calculate. There is some calculus of convergent series that we could use to calculate that. And if we did that, we'd end up with the intuitive result we had. So divide the payment by the interest rate and solve for the $80 that we'd have to put in the bank. So if we put $80 in the bank or into an investment that paid 10% a year, we could get $8 a year forever. So the present value of a perpetuity is just the payment amount, in this case 8, divided by the annual discount rate, because it's an annual payment. Future value of a single sum. Well, if we put $200 into an account today at 10%, how much would we have 2 years from now? Well, here's our calculator solution. n equals 2. The interest rate is 10%. Notice that we enter that as a whole number. Present value is 200. There's no payments. We're just going to accumulate in the account. So then we calculate our future value. It comes back to us as a negative number because we put the present value in as a positive number and get $242. Here's the algebraic solution. Whenever we want to move from the present period to the next period value using an interest rate, we just multiply by 1 times that interest rate. So for 2 years we do that twice, or we can easily write that as 200 times 1.1 squared, and we get 242. Now starting with 200, that's about a 21% rate of return. Remember that 10% compounds. So we earn 10% the first year on the 200, we earn $20. The next year we earn 10% on $220, which is 22. That's where the 42 comes from. So we're just using compound annual interest out into the future to get the future value of a single sum today. To get the present value, we just move back the other way. Instead of multiplying by 1 plus the interest rate, we divide by 1 plus the interest rate. So the question now becomes, in a more intuitive way, what would I have to put in an account today that earned 10% annual interest in order to have $200 2 years from now? And we call this the present value, or the present value equivalent of $200 2 periods in the future. So the calculations, again, there's 2 periods. We put in now the future value. There's still no payments, and calculate the present value. So if we put $165.29 into an account today that earned 10% compounded annually, we would have $200 2 years from now. And we can also show it this way, dividing by 1.1 squared, whereas we multiplied by 1.1 squared to go into the future. And we call this discounting. Now when we talk about an ordinary annuity, we mean a series of periodic payments that are all equal. A car loan, a home loan, making monthly payments or annual payments, those are all annuities. And we have an annuity function on our calculator. Now, the theory of it is straightforward. If we have 3 payments, 1 year, 2 years, and 3 years from now of $200 each, we could take the present value of each one and add them all up, and we'd have the present value of that series. And one way to think about that is, how much would we have to put in an account today that yielded 10% compounded annually in order to take out $200 1 year from now, $200 2 years from now, and $200 3 years from now, which would totally exhaust the account, just exactly exhaust the account. At the end of the 3rd year, there would be just $200 in there. But with the calculator function, we'll make it a little easier, because sometimes, clearly if we're looking at a 20-year bond that makes 40 different payments, a little cumbersome to calculate it that way. So, if we put our calculator in end mode, and that's the default mode in the Business Analyst 2 calculator, is end mode. And that's just telling your calculator, well, these payments come at the end of each period. So we've got $200 at the end of the first period, $200 at the end of the second period, $200 at the end of the third period. So we tell it that there's 3 payments, that our discount rate is 10%. Our payments are $200. We'll put those in as negative, and then our present value will come back as positive. Had we put those payments in as positive, our present value would come back as negative. Now, you should clear your time value of money functions, or we're going to need to put in that future value equals 0 here. With these annuity problems, that future value is what's left after the last annuity payment. And in our example here, there's no value past that. That's all the value there is these 3 annual payments. So set your future value to 0. I always do that with the time value of money function on your calculator. You've got 5 things. If you enter any 4 of them and solve for the 5th, I think it's good discipline and it'll keep you from making mistakes, because then you have to consider each input explicitly. Now what about the future value of an ordinary annuity? Well, this we would turn around to a problem more like retirement planning, where we're saying we've got an account and we're going to put in $200 a year from today, $200 2 years from today, and $200 3 years from today at the end of the second year. And how much would be in the account at that point in time? So that first $200 payment is going to earn 10% interest for 2 years. So that, remember, turns into $242. Our $200 that we put in 2 periods from now earns interest for 1 period. So that $200 would turn into $220. And then we get $200 at time 3. That's our third deposit into the account, but that's not going to earn any interest. So with our calculator, we can just add these up. 242, 220, and 200, we'd have 662 if we made these deposits into an account that earned 10% compounded annually. We can also put in n equals 3, 10% interest rate. Each payment is 200. Compute the future value and come up with 662. And again, here it's implicit that we've put in the present value is 0, because that's how much we start out with in the account. Now, in other retirement planning problems, maybe the investor has $1,000 in the account today, and then we're plotting payments out into the future. We could just put our present value in as that. In that case, make sure your present value has the same sign as the payments, because in that context, in a retirement planning problem, we're putting money into the account. We're putting $1,000 in today, and then 200, and then 200, and then 200. What's the future value? And that would come back with the opposite sign. Now, an annuity due is a way of referring to an annuity where the first payment is today. So if you won a lottery that gave you 20 annual payments, the first one would come the day you turned in your lottery ticket. And then you'd get equal payments for another 19 years after that for a total of 20 payments. So that would be an example of an annuity due. So our question here, what's the present value of $200 to be received at the start of each year for 3 years when the interest rate is 10%? So now we've got those 3 payments, but they're coming a little sooner in time than with our regular annuity. Well, there's a couple of ways to solve for this. Okay. Now we can do each of the individual ones. We've got 200 that's paid to us today. We take the present value of 200 a year from now and the present value of 200 2 years from now, add them all up and get 547.11. Now, we could also put payments equal to interest rate 10 minus 200 per payment. The future value is 0. And then compute the present value and get that 347.11 and then add 200. So what's going on here? Well, let me clear this out a little bit. What we've done is treated these 2 payments as a regular annuity. So this part right here, this 347.11, that's the present value of those 2 payments. See, n equals 2. So we've got, and this is in end mode, so we're getting a time 0 value. Well, we're also going to get $200 today, but we know the present value of that is $200, so we can add it to the 347.11. Now, another method is to put the calculator in begin mode. And the only problem with that is you've got to remember later on to put it back in end mode, or get in the habit of checking whenever you do a time value of money problem what mode the calculator's in. That said, when we calculate the present value of an annuity in begin mode, it gives us the value on the day the first payment into the account is made. So n equals 3 now, still 10%. Payments are still minus 200. Future value is still 0. We calculate the present value, and we can get 547.11 that way as well. So try to understand and get clear in your mind these two different ways in beginning and end mode, and why we can get the same answer both of those two methods. Now the future value of an annuity due, and this is an important point to remember, if you have your calculator in beginning mode for an annuity due, and you calculate the future value, it's going to give you the future value one period after, right? Because we're talking about the third period, but now that payment or deposit is at the beginning of the third period, the end of the second period. So let's take a look at solving for this. Now, $200, this $200 earns interest for 3 years. So we've got that times 1 plus the interest rate to the third power. This $200 right here earns interest for 2 years out to here. So there's our 2-year factor. And this third payment into the account earns 10% for just 1 year. If we add all those up, we see that that time 3 value, and again, get the intuition right on this. If we had an account, we put in $200 today, $200 a year from now, $200 2 years from now, how much would be in the account at the end of 3 years? That's your $728.20. Now, if we were in end mode, and we put in 3 payments of $200 each, remember, in end mode, it gives us the value right here. In end mode, that future value is on the day the last deposit is made. And so that's why we have to grow this. So we've calculated a time 2 value, then we grow it at 10% to get this time 3 value of $728.20. So that's another way to approach it. And now if we had your calculator in begin mode, then we wouldn't have to make that adjustment, because your calculator in begin mode calculates the future value after, 3 periods right here at time 3. So with the method 2 here, we're calculating that future value directly. What if we have uneven cash flows? Well, it's straightforward at this point. We've got some cash flow functions on the calculator, but essentially all we're going to do is take the future value of each of these deposits into an account to see how much it would grow to by time 3, which is where we're trying to calculate our future value. So we could take $300 earns interest for 2 periods. $600 earns interest for 1 period. The $200 comes right at time 3, no reason to grow that. Add them all up and get 1,223. Now we could do this with your calculator, and we're just saying, well, 2 periods at 10%, 300 turns into 363. 1 period at 10%, 600 turns into 660, and then we add $200 at time 3, add them all up, and get $1,223. And I don't know why that's hard to say. It doesn't seem hard to say. Okay, present value of uneven cash flows, just go back the other way. We discount this for 1 period, discount this for 2 periods, discount this for 3 periods, add them all up, and that's going to be our present value. Take a look at how we do this. Exactly that. 3 periods of discounting, 2 periods of discounting, 1 period of discounting, add them all up. We get a present value of $918.86. We could do that on your calculator as well. This seems a little cumbersome here. And we also have some cash flow keys on the calculator, and later on later topic review, we'll talk about how to use those. And there's some clear demonstrations in the Swayzer notes as well. And that's what this last note says. Can also use cash flow functions. We just put our first cash flow to 0, put all the other cash flows positive, and then calculate the net present value. Let's take a look at a mortgage example, how we can use some of this. What's the monthly payment on a $100,000 30-year home loan with a stated rate of 6%? Well, remember, that's our stated rate. If we've got monthly payments, then we need to divide that by 12. So when we divide that by 12, 6% over 12, we get 0.5% per month is our interest rate. How many payments? We're going to have 360 monthly payments over 30 years. Our interest rate, 0.5%. Present value is the amount we borrowed. Future value is 0 because we're going to pay the loan off entirely. It's an amortizing loan. Our monthly payments, our last one pays the loan off entirely, so future value is 0. We calculate our payment and see that it would be $599.55 per month. Now look at this second question. How much is the remaining principal or payoff amount just after the 85th payment is made? Well, one of the nice things about your calculator, I guess it's a nice thing, is that it keeps all that stuff in memory, whatever the last thing was in there. So now we know the monthly payment now, we just solved for it. And we're going to change the end. So if we've just made 85 payments, how many payments are left? Well, that would leave 275 payments left. And we're 1 month before that 86th payment. So all we have to do is change n and then compute the present value. So what we've done here is using that same interest rate, we've calculated the present value of the 275 payments that are left. As long as there's no prepayment penalties or anything, that would be your remaining principal and your payoff amount on the loan. So after 85 payments, how much principal have we paid down? Well, just over $10,000, right? $10,512. Paid it down to $89,488. Let's take a look going the other way now. Retirement savings problem. Our client has $75,000 in savings now. Retire 20 years from today. Well, in our notation, that's always T equals 20 periods from now. The client needs 25 payments of $62,000 a year to begin then. So first payment 20 years from today. The account's expected to earn 7% per year. So we have to calculate now, what is the annual deposit that the client must make at the end of each year for 20 years to reach her goal? So we've got $75,000 in there today. First, we've got to figure out how much we need at time 20 to make these payments of $62,000 a year for 25 years. So first we'll calculate that, and that's going to be our step 1. So how much do we need at t equals 20? Well, what we knew, we need to calculate the present value of those payments. Now, if we leave it in end mode, I'll calculate the time 20 value of 24 payments that come at time 21, 22, 23. Remember, in end mode, that present value function gives us the present value 1 period before that first payment, like an ordinary annuity. And so just as we did in one of our methods before, we'll calculate the present value of those 24 payments, and then we'll add the payment at time 20. So let me draw for just a minute here, just a second. Here's t equals 20 years from now. So we need 62K here, and at time 21, time 22, ... I think if we go out to time 44, that's our 25 payments. So this part, the 711.99, is the time 20 value of all of these payments of 62 each. And then we add that one to it to get the total amount we would need at time 20. Because if we look back to the problem here, it is clear. It says we'll retire 20 years from now and needs 25 payments of $62,000 a year that begins then. So it's really an annuity due valuation at time 20. And so that's our 773.99. If we put it in begin mode, we'd just put n equals 25, and we could calculate the time 20 value that way. So either way, we find out that we need $773,099 at time 20 in order to make these retirement payments, 25 payments of $62,000 each. So now we know how much we need then. The second step is now to solve for payments, right? So here's our future value. That's a time 20 value. Our interest rate is 7%. We're going to make 20 deposits, but we already have $75,000 in that account. So we're going to solve for the payment that we need to make every period for 20 periods if we had $75,000 in the account today. And we solve for that payment, it's minus $11,778.68. So if we had $75,000 today, the account pays 7%, we'd have to put in $11,778 a year from now and every year for 20 years. And at the end of that 20-year period, because the calculator's in end mode again now in step 2, that future value is the day the last deposit's made 20 years from now. And those payments would have to be $11,778. Notice they're the same sign as the present value as what we've got in the account today. In an odd problem, if that came out positive, what would that mean? It would mean that we had more than enough in the account today to do that, and that you could actually take money out each year. I doubt if you get a problem that tricky on the exam, but this may help you get a better grip on these signing conventions. What's in the account today plus our deposits, those should all be the same sign. Now let's do a couple other calculations using our time value of money keys. Elmer has won his $4 million state lottery and has been offered 20 annual payments of $200,000 beginning today, or a single payment of $2,267,000. Wouldn't it be nice? What is the annual discount rate used to calculate the lump sum payout amount? Well, what are we given here? We've got monthly payments. We've got a present value. Our future value is going to be 0. We need to calculate what discount rate would make the present value of 20 payments of $200,000 equal to $2,267,000. Well, it's kind of an annuity due, so how are we going to handle that? Okay. Well, we can put this in begin mode and just say, well, there's 20 payments, future value is 0. We want the present value to be this. Or we could have these payments. What's the interest rate? If we compute the interest rate, come up to 7%. Last thing we want to take a look at is calculating n here, and I have a little caution for you. If you're using the HP12C calculator, n is always rounded up. If it takes you 3.1 years to get to your amount, it'll tell you 4. Now the exam writers know this, and it shouldn't be a problem. I just don't want you to get surprised if you use the HP12C and you always get a whole number. The TI calculator, on the other hand, will give us fractional periods or fractional years. So now, Elmer has won $4 million again and has been offered these 20 annual payments or a single payment of this. Now what if this were an odd lottery where Elmer could choose the amount of his annual payout based on a 7% discount rate. Let's say his payments, instead of $200,000 a year, and this is an odd question, I know, but we can still illustrate the point with it. If we had, let me reword it. If we had $2,267,000 in the account today, how many years could Elmer draw payments of $232,631 if the interest rate were 7%? So again, we've got the four pieces, right? We've got payment, we've got the interest rate, we've got the present value and the future value. What we don't have is how many payments. So in this case, we can solve for n. Now again, it's an annuity due because the first payment comes today. So let's put it in begin mode. Future value is 0. Here's our payment. It's opposite sign of the present value. Our interest rate is 7%. We compute n and find out n is 15. So at an interest rate of 7%, 15 annual payments of $232,631 have the same present value as 20 annual payments of $200,000. So that ends this topic. The things you want to focus on, make sure you can do these. Present value of an annuity, future value of an annuity, present value and future value of single sums, present value of a perpetuity, and understand how your calculator works. That in begin mode, it's giving you present value on the day the first payment is made or first deposit is made. In end mode, the present value gives you that value one period before that first payment or deposit is made.